Hi, this is an overview of ECE 494-761, a course called Advanced Controls Robotics. Now, 761 is one of the courses offered on Bison Academy. This is the semi-official website for the Electrical Computer Engineering Department at NDSU. Go down to 761. That takes you to the syllabus for this course. Now, on this website, you've got all the lectures in PDF format, the recorded lectures as a YouTube video, sample code, and the homework sets. And the topics covered are basically the mathematics behind modeling and controlling robotic manipulators. Now, starting out, what we'll look at are translation and rotation matrices. Now, almost all the material in this course uses MATLAB very heavily. With MATLAB is not designed for animation, but it does a really good job at it. With translation matrices, you can move an object in the x direction, y direction, z direction. With rotation matrices, you can rotate the object about the x-axis, y-axis, and z-axis. Now, this is important in robotics because to describe a robotic arm, I've got to move from one joint to the next, that's translation, as well as rotate. The second topic we'll look at are reference frames. So for a robotic arm, typically you define reference frames at each joint, like we've got the shoulder, the elbow, the wrist, the fingers. To go from reference frame to reference frame, I've got a translation and rotation. The way you define the reference frames basically defines the robot. It tells you where each joint is as you move the robot. Third topic we look at is once we have reference frames, once we have translation rotation matrices, we start looking at forward kinematics. Forward kinematics looks at how to define where the tip is, given the joint angles. What that lets you do is, in this case, this is a RPR robot, rotate about the first link, translate about the second link, rotate about the third link. I know where the tip position is, given where the three parameters are. Rotation, translation, rotation. That's forward kinematics. Inverse kinematics is going the other way. If I know where the tip is, what are the joint angles? Now, forward kinematics is pretty straightforward. It's just a bunch of sines, cosines, translations, rotations. Inverse kinematics gets kind of tricky. If I know where the tip is, what are the joint angles? What you're trying to do is you're trying to solve nonlinear equations with multiple solutions. It's kind of tricky, but it is necessary because if you ever want to know what angles put you at a certain spot, you need to know inverse kinematics. Next topic we look at is path planning. With path planning, I want to go from point A to point B to point C. How do I do that while keeping the joint velocities finite, while keeping the joint accelerations finite? And there's several different methods that we look at. There's spline interpolation, cosine interpolation, and so on. What that does then is once I define the path that I'm supposed to follow, in this case the green ball, I can tell you what the joint angles are that follow that path. And I want to choose the path in such a way that the joint velocities and accelerations remain finite. Next topic covered are dynamics. Ultimately, we want to get to the control of robotic arm. To do that, I need to know what the dynamics are. So here what we look at are the dynamics of a two-link arm. This is essentially a three-link robot arm where you fix the base. The math behind a two-link arm is fairly nasty. It's about a 3-page derivation. A three-link arm is about a 10-page derivation. We'll just stick with 2 dimensions for the remainder of this course. In 2 dimensions, I want to come up with the dynamics, and this would be like a two-link arm in free fall. Next topic are controls. With controls, what you're trying to do is to find the joint torques to follow a prescribed path. For example, I've done path planning and defined how I want to go from point A to point B. That's the light blue robot drawing out the green square. The control is trying to force the actual robot, the blue one, and the tip position in pink. Control it so it actually follows the desired path. Now when you do that, I've got gravity pulling the robot down, I've got Coriolis forces, other forces like that. If I start to cancel them, I can get better and better tracking. Those are feed-forward terms. Next, we look at Jacobians. Jacobians do several things. They relate tip velocities to joint velocities. They relate tip forces to joint torques. With Jacobians, I can control the tip position of a robot in XYZ coordinates rather than the joint angles. It's another way to control the tip position of a robot. But what Jacobians also do is they let you model impact forces. If the robot hits a surface, the force on the wall translates to the joint torques through the Jacobian. In addition, I get kind of a weird phenomenon. If I have n degrees of freedom in free space, I lose 1 degree of freedom when I come in contact with the wall. And what we'll try to do is simulate what happens when a robot arm hits a surface. For example, here, I've got a robot arm trying to follow the green one. It hit the wall, the dotted line, that imparted an impact force, along with the force on the wall. When I come off the wall forces, of course, go to 0. I'm in free space. So we'll look at how do you model impact forces as well as forces when you're in contact with the surface. So that's kind of what we'll be covering in this class. It's the mathematics behind the modeling and control of robotic arms. After taking this course, you should have a basic understanding of those mathematics. And hopefully you'll have some fun with MATLAB animations as well. Again, MATLAB isn't designed for animations, but it does a pretty good job at it. And if you can get the animations, the MATLAB code to work, you'll have a basic understanding of the mathematics. So that is ECE 494-761, Advanced Controls Robotics. If you're interested in this material, please consider signing up for this course.